Well, good afternoon, everybody. This is Roger Frechette. I'm the managing principal of Interface Engineering, and I am here today to welcome you to the next installment of Interface's High Performance Buildings free webinar series. And just a quick couple quick notes. If you are not familiar with Interface Engineering, Interface is a national mechanical, electrical, plumbing, fire protection design firm. We've been in business for 51 years. We have 7 offices located across the United States, including one downtown Washington, D.C. We provide engineering services for commercial, residential, academic, healthcare facilities, and many more. We have a very strong focus on sustainable design and high-performing buildings, hence the reason for putting together this year's webinar series focused on high-performing buildings. So today we have a very special treat for you. We have Mr. Scott Macucci, who is Macucci. I'm sorry.
Macucci. There we go.
Scott Macucci, and Scott is a senior lighting designer with us at Interface Engineering. He's a licensed professional engineer, and Scott has more than 20 years experience, nearly half of that with us at Interface. He has extensive experience in commercial, residential, academic, K through 12, secure facilities, and industrial projects. Scott has his bachelor's degree in architectural engineering with the University of Colorado, Boulder, where he had an emphasis on lighting design. And Scott is a member of IESNA, which is the Illumination Engineering Society of North America. So with that, Scott, please take it away, and thank you for being our presenter today.
All right, thank you, Roger. And again, thanks everybody for joining us for the presentation. Today we're going to have an introduction to lighting. And so of course, in the study of lighting, there are many scientific topics you can really delve deep into. And there are also, with regards to architectural lighting, there are a lot of aesthetic and subjective topics you can delve into. Our study today will be more technical in nature and kind of end with a couple of case studies where we can look at applications. And so I'll just get going. We have quite a few items to discuss here. So first, the course is registered with the AIA. So by attending today, you're eligible for 1 learning unit there. And so quickly, the course description is we're going to gain a knowledge of light, the human visual system. We'll also discuss lighting terms and applications, specifically as they apply to architectural lighting systems. So our objectives are to attain a technical understanding of light and the human visual system. We want to understand lighting metrics and terms that we use when we're discussing architectural lighting design. We also want to understand, the energy codes, their goals, why they are here, and kind of give a brief overview of the requirements within them with regards to lighting and lighting controls. And then we'll review some strategies for minimizing energy use for lighting systems. So first, we want to talk about,
Scott,
what is light?
I'm going to interrupt you real quick. I'm not sure that your actual presentation is being projected. If you could check.
Are we? All right, let's see. So are we having the same issue we had?
Yeah, you were close. It came up for a second. There you go.
So are you seeing some movement here? Okay, so we're rolling along. Okay, sorry about that. So we want to first define, what is light? Light is electromagnetic radiation, it's energy, and in particular, the portion of that spectrum that our visual system is sensitive to, that allows us to see. Of course, the electromagnetic spectrum, it spans many, many, many wavelengths of energy. So way down to cosmic rays, which are very, very tiny wavelengths, up to very large wavelengths, 3,100 miles for a wavelength. So somewhere in the middle of there is a portion of the spectrum that our visual system is sensitive to. And that generally ranges from about 380 nanometers up to about 740 nanometers. And the specific wavelengths we relate to specific colors. And so on this chart here on the bottom, the central curve depicts our general sensitivity, the visual system as a whole, to specific wavelengths of light. On the upper right, we kind of break that down because our visual system, we actually have two different types of photoreceptors that we use for vision. And so one of those we use for daytime light levels, which we would call photopic vision. And we see this curve here, this lower one kind of shifted towards the middle. And we also have our nighttime vision, or low light levels, which we call scotopic vision. And we can see there's a curve here that is shifted slightly to the left, a little more towards the blue. And as we can see, it's much more sensitive to the radiation than our daytime vision is, which is kind of you expect because low light levels, we need to be very sensitive to see those. We'll get into more detail about the photoreceptors as we move forward. So we want to talk about light as it applies to human interaction with architecture. So this seems pretty intuitive, but it's important to say because what we see is the light that bounces off of surfaces. So how the light hits the surface, as well as the qualities of that surface, they dictate what we see. So is the light diffuse? Is it a very direct beam of light? Is the surface specular in nature, what we see in a reflected image, or is it diffuse, where the light hits it and then it breaks up the light as it bounces off, possibly even absorbing certain colors of the light that's hitting it and only projecting other colors. And it's important to say that because a lot of our codes and even the IES recommendations are related to illuminance, which is actually this portion is the light hitting it. And we'll get into more detail about that later as well. But we also need to think about light as it applies to the tasks we are performing. So, the pictures here depict many different types of tasks. We have a nighttime illumination, the pathway, security is very important. We want to be able to see people or animals possibly approaching us from a distance. It's very dark around you. You want to be safe. In a gym, you need to identify fast-moving objects that may be hanging up in the air or maybe even on the floor, versus working in a manufacturing facility where you have very specific detailed tasks, and you might be standing next to moving equipment that can be very dangerous. So, and et cetera. We have many different applications, and all of these require a different quality of light. Where's the light coming from? Do we have shadows? And what our contrast ratios are. So before we can really talk about architectural lighting, we need to know how does our visual system work? And so this will be a brief overview of this. Of course, we can delve deeply into these components. But in a general sense, we have three components. We have our eyes, which are receptors. The light is coming in to our eyes. We have the optical nerve, which transfers a signal from the eyes back to the final component, which is our visual cortex. And so I'll just keep referring to that as our brain, which evaluates all the signals that we're receiving from the eyes. So looking closely at the eye, we have these components. It is the receptor of visual stimuli. So light comes in and lands back here. So, it passes through our cornea and through the pupil. So the pupil, of course, gets larger or smaller as the iris opens and closes. And that is our visual system's method for adapting to different light levels. If it's very bright, the pupil will be small. If there's not very much light, it opens up to allow as much light as possible into the eye. Of course, the lens, it will contract and expand by use of the ciliary muscles to focus our beams back here onto the retina, and specifically the spot in the middle of the retina, which is the fovea. So our lens, again, will bring light in and it will focus the image back here on the fovea. There's also stray light that will come and hit other portions of the retina, which is on the back here. And those are essentially your peripheral vision. Interestingly, the retina houses all of our photoreceptors. There are multiple layers to the retina, and the receptors themselves are actually on the back side of the retina. Now, one thing we'll also note here is the optic nerve connects to our eyes, as we saw in the image before, and it connects in this general area on the retina. So when we talk about the photoreceptors themselves, we have two different types. We have what we call the cone receptors, which we use for our photopic vision, the daytime highlight level vision, and color. And then we have three types of those, and we'll look at those in a minute. And then we have one rod receptor, which is really our low light level photoreceptor. And they are aligned on the retina back here. And interestingly, again, is we have both receptors along the entire retina, although the fovea has no rod receptors. So none of our low light level receptors are in the fovea, which is where the image is actually focused. Only our cones are in that space. And the cones that are on the rest of the retina are much less dense than the rods on those. So that's an interesting fact as well. So again, looking at the receptors, we mentioned we have the cones for daytime and our color vision. And there are three types of those. And so the graph down here, it actually is graphing the sensitivity of all four. So we have the three cones and the one rod type receptor on this chart. And so we see that we have one cone that's sensitive in this area of the spectrum, and we generally refer to those as the red cones. And we have the next one, which is green, which is just a slight shift towards green. And then the other cone, we have this blue cone, which is shifted way down to the left. Again, the black line represents the sensitivity curve for the rods. Now, this is a normalized plot, so they're all peaking at the same spot here. So what we find really interesting about this is, you know, intuitively, you expect as a certain wavelength of light enters our eyes and lands on one of the cones, we're getting a signal, and you might expect that a signal here at 500 nanometers comes in, hits this receptor, and the receptor is telling us, hey, this is kind of a blue light, right? And we'll send that back to the brain. When in reality, what these curves represent is just the sensitivity of that specific cone at all these different wavelengths. So for this red cone, at 500 nanometers, we'll get a signal that's associated with this amount of sensitivity to that. So, you know, the signal here would be lower than the signal from a wavelength from here. However, the signal at 500 nanometers, this cone will send the same signal to the brain if it sees light from this wavelength, which is going to be somewhere around 630. It's a very interesting thing that the cone itself doesn't tell you the color. What tells us the color of the light is our brain's evaluation of the signal from all of these cones together. So again, at 500 nanometers, not only are you hitting this red cone receptor, we're also hitting the blue at this very low level. We're also hitting the green, and we're hitting the rod. So all of the receptors are sending a signal to the brain. The brain's evaluating the level of every signal, and then that is what tells us our perception of the color. So one interesting fact is, again, I showed you that the cord that connects your cortex to the eyes actually attaches to your eyes on the retina. And what this results in is that we all have a blind spot in each one of our eyes. And you can experience this with this very simple test here. So being that the plus is on the right side, if you cover your right eye or you close your right eye and you focus your left eye on the plus symbol, depending on how far away you are from your screen, as you move in and out, the dot will disappear. If you move your eye slightly to the left or right, it'll come back into play, or if you move forward or back. And it pops right out. It's really an amazing thing if you've never seen this before. So, you know, not only is it interesting that we have that, but it's also interesting to realize that, you know, if I close my right eye, I don't see a blank spot in my vision everywhere I look. And that's because the brain is filtering out that portion. the big message here is that your visual cortex is really what is creating all of our perception based on signals from our receptors. So the cortex, we have one on each of our brain, and they each receive a signal from both. So, the green one here follows here to the left side, even from the right eye, but also the left eye sends a signal to the left side of the brain. So, the cortex is evaluating the data based on the momentary stimulus that we're receiving, what light is hitting our eyes right now. But it's also referencing our past experiences. If you've been in, say you've been on a boat out on a lake, and at first your legs feel a little bit wobbly, getting used to the waves constantly hitting the boat, and then you go out for a couple hours and you come back on land, and all of a sudden it feels like the land is wavy. That is your brain using, your recent experiences to tell you what to expect. It's the same thing, vision, and that relates to color. It also relates to our experiences as we've interacted with our physical world. You can imagine approaching a building from the outside. You see a door. You walk in the door, you expect to see the interior of a building, right, with probably a horizontal ceiling and vertical walls. You would not expect to walk in there and see another outdoor environment or just the other side of a wall. Your brain is using your previous experiences to determine what you expect to see, and that, in effect, alters what you actually do see. So another keynote is that our visual system is very, very interested in visual contrast, right? It's not looking for things that are the same. It will identify differences in brightness, color, or physical location. So if something's moving, our visual system will pick that up. I always find it pretty amazing that we can see a plane that's flying in the sky at thousands of feet up in the air. And really it's because it's moving in the air. And number one, you may not expect something that high to be moving in the air, versus watching a bug fly around that may be only 50 feet from you. We expect that. It doesn't draw a lot of interest. See a tiny little speck, and it's very, very small in our visual field, but we see it very easily. Our brain will also normalize static or consistent visual inputs. And so that relates to, if you look at the same thing, stare at it for a long time, and then you look away, you'll notice that the colors are juxtaposed, right? Partially that's due to our cones being saturated, but it's also our brain has normalized that as a normal experience. And when you change it, things look different. One thing that also happens is what we perceive is affected by what is around the object of our focus. So, one example of that is how we normalize constant color and motion. This color chart here, we can see that at the top we have these blue pieces located in between a black surround on these lines, whereas down below, the blue pieces are surrounded by white surrounds. You may have seen things like this with, just black squares and white borders around them. But what we see here is that the appearance of this blue appears lighter than this blue here. Whereas I can show, if I can get this to pop in for me. All right. So as you can imagine, if I move these blues away from there and I put them together, we can see that the blue is actually the same color. However, when we pull them back into the diagram here, we can see how it takes on those qualities again, where just because it's surrounded by black lines, it looks darker than the lines that are surrounded by white lines. So let me get that. All right. So, so what are our takeaways? I mean, I really enjoy optical illusions, and I could spend hours finding multiple versions of those things and talk about how our visual system is interpreting signals. But we're talking about architectural lighting here, right? So our takeaways from reviewing the visual system is that our system allows for adaptations of brightness and color. At daytime, maybe 10,000 foot candles outside. Inside during the daytime, we're generally in 30 foot candles, maybe 50 foot candles, very low. But even lower, you might go outside on a full moon night and have 0.1 foot candles and still see very well at that time. That's a huge range of adaptation for brightness. We are very sensitive to contrast. It's our means for being safe. It allows us to perform tasks. And contrast also will elicit motion and create visual interest. And because our recent experiences define our expectations and the fact that the surrounding environment impacts our perception of what we're focusing on, we can't have a one-size-fits-all approach when we are recommending things like light levels or color, because all these different things affect it. All right. So let's get into some lighting terms. And so again, these are terms we would use when looking at architectural lighting. And we'll start with the lumen, which is, of course, luminous flux. It's an energy. It has a time component to it, but it generally relates to light output out of luminaires. So, you can imagine as a 25-watt lamp would have a certain output associated with it in lumens, and a 60-watt lamp would have more. So the lumen is simply the light output. It relates to the energy in those wavelengths of light that we're sensitive to, but it's weighted by that curve we saw that shows how sensitive we are to different wavelengths of light. So if you have 100 lumens and it's all in the range of red light, we would be less sensitive to that. And it wouldn't actually be lumen. I guess I should say the radiant energy is all in the red wavelength. The lumen value would be lower than that same amount of radiant energy in the green spectrum, which we're very sensitive to. So moving from there, let's talk about intensity. So intensity deals with how many of those lumens are packed into a specific solid angle. So a solid angle is essentially, if you looked at this in 2D, you have an angle. Well, if you translate that to a 3D piece, it looks like a cone. So how many lumens are packed into that little cone? If this light source had 100 lumens coming out and it came out in all directions evenly, you can imagine the intensity in this direction from that light source would be way lower than if we took all 100 of those lumens and packed them all inside this little angle. So that's what intensity is about. The next term we talk about all the time is illuminance. Now put it in red because, again, most code references deal with illuminance values, as well as a lot of the IES recommendations, although the IES does not stop at illuminance. It's very important to know. So illuminance is how many of these lumens from this light source are falling on a specific area. So the units are lumens per square foot, which we call the foot candle, or in the case of the metric system, lumens per square meter, which we call lux. Again, it's lumens that are incident onto a surface. So in this diagram, we come down here, what is falling on the surface is what we would call the illuminance. Whereas the luminance relates to the light that's bouncing off of this surface in a specific direction. So for us, when we see this surface, we're seeing the brightness, we're seeing the luminance value, and that relates to brightness. Another term that's thrown around a lot, although sometimes interchangeably with efficiency, is efficacy. Efficacy deals with any time where you are taking one form of energy and creating a different type of energy. So in our case, we're taking electricity and we're creating light with that electricity. So electricity comes in, we have light coming out, we also have heat coming out, and we also might have other types of energy. In the case of an LED, maybe we have radiant energy that has wavelengths that fall outside of our visual perception of those wavelengths. So maybe it's UV radiation. That would be part of the other energy there. So how efficiently can we take one form of energy and create another form of energy? That's what we call efficacy. And it's one of the prime metrics when we're looking at light sources, which we'll look at here in a minute. When we're talking about luminaires, that's when we talk about efficiency, right? So in a luminaire that might have a reflector around, say, an incandescent lamp, the lamp itself creates a certain amount of light, say 100 lumens. But the fact that we want all those lumens coming out in one direction, we have to redirect some of them. And so we lose some of those lumens when they bounce off the surface. Sometimes they'll even bounce back towards the lamp. So efficiency is a comparison of how many lumens does this lamp have to how many lumens actually come out of the fixture itself. All right. We also throw out distribution terms. Certainly lighting designers do all the time. And they fall into general categories. You know, when all the light is coming down below horizontal, we call that a direct light source. When all the light is shining up above horizontal, we call that an indirect light source. When we have a combination of those things, we might call it a direct indirect if we have more light coming down than we have coming up, but not anything really coming out horizontally. The opposite case would be an indirect direct, when we have most of the light coming up. And when all the light is coming out in all directions, we would call that an omnidirectional light, maybe a general diffuse light. There are different terms for that one. All right, so next we want to talk about color. So we're very familiar with the fact that all the lighting we see, even natural light or artificial light, has a color associated with it. So we refer to that as the color temperature of the light source. And it is defined by an ideal black body radiating a wavelength of light when it is heated up to specific temperatures. The ideal black body is actually not a real thing, it's a theoretical item. But because the temperatures are so high that we're dealing with, we use the Kelvin temperature scale. And so this graph represents a plot of our color field. You know, these are the colors that we can see. Around the edge are the wavelengths of light. And this line in the middle is the path that shows the wavelengths of light that will be emitted by a black body radiator when it's heated up to these specific Kelvin temperatures. So for instance, at 4,000 Kelvin, an ideal black body would radiate light that produces this kind of color right here. And so light sources try to follow this curve when creating light for architectural applications. One thing to note is we can see this line for 4,000, it crosses the curve, right? So technically, you could have a light source with this color be rated at 4,000 Kelvin, and also at this color, it would be rated 4,000 Kelvin. So the idea is that these are so subtle that you do not pick them up. But we do need to keep in mind that the visual system loves to see contrast, picks up variations very easily. So what do the color temperatures look like in an architectural sense? This graph is really good. It shows, you know, the differences as you step up in color temperature. And oddly enough, you know, the higher the temperature, we refer to it as a cooler light because it turns blue. And of course, when they're all next to each other like this, it's very, very easy to see the differences. However, if you were to cover up all but two adjacent slides there, you'll see that the difference is a lot more subtle, a lot tougher to pick up. So that's one thing to keep in mind in an architectural setting. Generally, you do not have this tight of a spacing and to see that contrast. But so we want to also look at, you know, what are some references that we have for color temperature? We'd love to design architectural lighting in that 3,500K range, maybe 3,000, even down to 2,700. 4,000 is actually a very common color temperature to use for interior lighting applications. It's interesting to see that, you know, when we look at this graph, it looks very white, whereas it's often referred to as a bluish light source. And again, I think that's because we're seeing a very blue on this end. This looks very white in comparison. But looking over here, we can see some references to nature. So a blue sky is at 10,000K. So that's a very, very blue light. When we look at a cloudy sky, it comes in at 6,000K, still very much on the blue side. Direct sunlight, you'll see some different references here. You know, we have 4,800K here. I've seen some that list it at the, you know, 5,300 Kelvin color temperature. Again, higher than you might expect because direct sunlight, we really kind of relate to this more warmer color. And then as we come down here at the very bottom, you know, a candle is at 1,900K. So I always find it very interesting to talk about color temperature. Again, we know we like to design to kind of these color temperatures, and it's always really considered to feel a little bit more comfortable, a little more cozy when you have a warmer color temperature versus a blue. And, you know, that's possibly related to the fact that historically we've had electric lights for maybe a little over 100 years. But before that, we had hundreds of years using candlelight, maybe burning gas. And even when electric light came out, it was electric light that was incandescent, which is literally heating a filament to the point where it will glow. So we would use those more at night, right? We didn't have them during the daytime. We didn't use those light sources during the day, which when we experienced our light in this type of color. But then when we were cozy at night and coming indoors, we had the warm light. And that's kind of stuck with us for indoor lighting. All right, next thing to discuss is CRI. So this is color rendering index, which essentially is how naturally does your light source render colors. It's actually specific to comparing it to light at a certain color temperature. But in general, you can say, sunlight is natural, right? So we're trying to compare everything to what sunlight does. Incandescent light sources tend to be at 100%. They'll render colors very naturally. Whereas all of our other color light sources don't. We'll see CR values, they range from 0 to 100. And so 100 being completely natural. And we tend to see the ranges in the 80s to the 90s for artificial light sources that we're using now. And they determine that by having observers look at these color patches and compare different light sources, looking at these color patches and compare them to natural light when they see them under an ideal light source. So it's a limited color palette. And what one of the limitations is, well, if it's not 100%, we know it's not as natural, but what's different about it, right? We really can't tell. We can just tell that it's not natural. So the lighting design industry is actually moving towards the IES TM30 guideline, which has, number one, many, many more of these patches to look at. And number two, it also has a reference to what they call Gamete, which is a graph and an image that tells us how does the light change compared to natural. So fidelity is essentially what we call CRI. So how natural does the light look? When that's at 100, the Gamete is 100. There is no shift in anything. But as the fidelity starts to drop and it becomes less natural, the Gamete tells us, well, does it get more saturated? Like, are the reds too red? Or does it start to look gray? If it's above the line, it's more saturated. Below, it's gray. And then this color graphic will actually even tell you which specific colors are being shifted. So this gives us much more information. It's just starting to pick up steam. But when you see it, this is what we're talking about. So it's actually very beneficial. I'm going to kind of blow through the luminary types here. Again, I have a lot of subjects here, and I tend to talk a little bit too long. So I want to get to all the good stuff. This is just a brief review of luminary types. Of course, we have downlight, very small. Surface mounts vary greatly. Troppers would be a recessed, generally a 1 foot wide by 4 foot or more. A recessed slot is like a tropper, but very narrow, but they're built actually completely differently. We have some of these other types that are specific for specific applications. And briefly, I just give you an example of a cut sheet. So luminary cut sheets. The goal of that is to show us how is this luminaire constructed, what is the performance of the luminaire, what is the outputs, how can we specify this, how can we build a catalog number, and it also tells us about finishes. Are there any integrated controls, and do we have the opportunity for integrating emergency lighting? So I'll do a brief overview here of light sources, starting with the sun, right? We use the sun first. And this shows here that the sun has a continuous spectrum, and they're relatively even across the board. We have some references here to a north sky, what the spectrum looks like there. Again, at 10,000 K. The sun and sky is the one with all the colors in it at about 6,000 K. And then the sun alone, again, at 5,300 K. So that's the 5,300 reference. So the advantage of the sun is, of course, it's very efficient, right? We don't have to do anything to get sunlight. It's very inexpensive. It's very high on the color rendering index because it is natural light. And it also has health and wellness benefits. I'm sure you've heard about circadian rhythms, even vitamin D and sunlight. The cons are it doesn't work at night. There's a lot of heat gain associated with it that comes into your building if you do not control it. And there can be excessive glare and brightness because the sun is very, very bright. an incandescent light source. After we went through candles and gas, we had incandescent light. So again, we're heating a filament to the point where it glows. We see that it also has a very continuous spectrum, although it's really weighted more towards the red end of things. And again, seeing our curve, we're more sensitive to lighting in this range here. So the output, it's an inefficient source of light. It's also very hot, and the life rating is very short there. However, the CRI is 100. It's a very good color quality. When it dims to warm, which is very comfortable for us. And also this filament is very small, so it allows us to control the light from this source very easily, at least when we have a clear bulb around it. The next source of light that we used quite a bit was fluorescent. And I say was, but we still have a lot of it, but we're not designing the fluorescent very much. The first thing that jumps out is the spectrum of this. It's kind of even, at most levels, but it spikes in very specific wavelengths. And we would consider this what we would call a triphosphor lamp. So, light is created in here by having mercury in this tube with some inert gases. We punch it with a high voltage to get an arc started in there. The arc excites the mercury, which emits UV light, which would not be safe for us if not guarded. So then we have phosphor on the bulb itself. UV interacts with the phosphor, and the phosphor produces light. And the phosphors produce light in a narrow range, so you have to have many phosphors to get a full spectrum. So these offer much better efficacy, so lumens per watt, than incandescent. The life rating of this is very good, 10,000 to 20,000 hours. But the CRI dropped, right? It dropped to about 80. You can get 90 CRI fluorescent lamps as well, although light output tended to drop as you went up in the CRI. The cons of this are that it requires recycling. We cannot just throw mercury out on the ground. Not all fluorescent lamps are equal. Some are very bad, some are very good. Warm-up time can be an issue. These do not start out at top brightness. If it's cold outside, you'll never get to full brightness. And then this large luminous surface actually creates a bit of a challenge to control this light and focus it where you want it to go. High intensity discharge. So these lamps are used, when you need a lot of light, typically outside or gymnasiums, high mounting heights. They also had a very high efficacy, up to 100 lumens per watt. Decent life. They also can have CRIs of 85, although a lot of them do not. A lot of them, the CRIs are more in the 60 range. Output is very good, and it is closer to a point source than the fluorescent. However, warm-up time on these was really horrible. If you shut it down, it had to cool down even before it could turn back on and warm back up. Again, we had to recycle it because of the chemicals that were in the tube here, and the lamps could be very expensive. So, what we see now on all new construction projects is LED, right? So I'm jumping right to the current white LED. I'm skipping our transition to where we are now with the older LED sources, which could have been very unreliable, not very good dimming. But right now, our standard, these have the best efficacy. We're looking at luminaires, like the whole luminaire that has an efficacy of 120 lumens per watt. And it's going to just get better. The source itself, LEDs by themselves, are already up at 200 lumens per watt, which is pretty amazing. Life ratings, 60,000 hours is what you're going to see on those cut sheets. And most manufacturers will tell you that you will get more than 100,000 hours out of the chip itself. The CRI's range, it is, the way we produce light with an LED is it either comes out as a blue, red, or green LED, and sometimes you have to either put a phosphor on that, right? So we're back to the phosphor creating the additional wavelengths of light, or you put all three of those colors onto a chip and you mix those colors to create white light. So the CRI can range. We do have to be careful about our CRI options when we're specifying LED lighting. There are increased options for color temperature. You can literally get almost any color temperature that you want from the LED light source. It's now the standard for new luminaires. Most manufacturers stopped even researching fluorescent technologies and design years ago. The control consistency is much better now. We standardize on a 0 to 10 volt control system. Problem is these can be expensive. They can be confusing to specify because there's so many options available. And if you don't keep them cool, they will die quickly. This one here is just a note to say that because the light comes out in a directional sense, we don't have to redirect it very much. So the luminaires can be very efficient. They like to be cold, so outdoor applications are not a problem anymore. This chart, again, is just a reference to the fact that LEDs right now are much higher, and this is for a whole luminaire. These are for lamps themselves. They would actually be even lower when you stick them in a light source in a fixture, which is going to block some of the light. So I want to touch on energy codes. This will be, again, a brief overview here. Just wanted to kind of really indicate, we all deal with the energy codes. What is the purpose? The energy codes from a lighting standpoint really overall are to reduce the energy use index of buildings. Partially, it is for sustainability, right? We want to take care of our planet. Our country has decided to, take a lead in that role. But also, it's a way for our, from a country standpoint, to not rely on resources from other countries. We don't have to import. So we want to have energy independence as much as possible. So those are really the two main goals of it. So, how do we do it? What's the criteria for it? Well, we need to reduce our lighting power density. So how much power in watts do we have in our buildings? And then also we want to reduce the actual energy, right? So power energy is kilowatt hours, right? So the power times the time that light is on. So we want to provide controls as well to turn lights off when we don't need them. This chart was just to really indicate, federal mandates that all states adopt a code. And so generally you can choose from the IECC set of codes or the ASHRAE set of codes. This is a chart from the Department of Energy website that shows what states have adopted what codes. It's interesting to note that in our area, within say 20 miles, you could be dealing with a state that has adopted the 2015 IECC or the 2012 IECC or ASHRAE 2013 or even the 2018 IECC. So, we always have to be careful, where are we and what code are we dealing with? Beyond that, some states have their own codes. California, Oregon, Washington, they have their own set of energy codes. So what do we deal with energy codes? Again, one is the lighting power density. How many watts can we have in a specific space? This is just a small snippet of one space type out of the ASHRAE energy code, showing that, if we have an office and we're doing a space by space type, we can have 1.11 watts a square foot in an enclosed office, and an open office, 0.98. The RCR threshold deals with, how tall are your ceilings. If you have really tall ceilings, you can actually get some additional lighting power. The rest of this section here deals with controls. Anywhere you see an REQ, it's a requirement. If it's an add, we get to choose one of these two options, but one of these is still required. So we can see there are actually many different requirements for controls. They're really pushing more on controls, again, because energy use in kilowatt hours is really our prime goal. All right. This chart, as you would imagine, our lighting power density allowances have gone down over time. This is really just to show that, it really relates to what we have available. If technology has gotten better, the efficacies have gone way up, and we can ratchet down these maximum levels. And I'll show you in a minute, they're not necessarily restrictive to us. And it's also one of the goals of the entities writing the codes that they allow you to comply with them without being under any undue stress financially, right? They don't want to make it hard to implement the codes. So generally, what the codes will tell us, again, beyond lighting power density, is controls. And what we see are you're going to have some combination of occupancy sensing that will turn off or dim lights when you're not there, time clock control that will sweep lights off, generally with an override switch that you can turn on for 2 hours at a time, and controls that allow you to manually dim your lighting system. And just to briefly touch on, there are, of course, voluntary programs that go beyond energy code levels for sustainability. All right, so let's look at a couple lighting strategies, and then we'll finish up with a couple of case studies. So, what are some strategies to reduce your energy use? Number one, we can use efficient light sources. we have LED now, it's standard, let's use LED. You know, let's not go back to a fluorescent source. We want to apply light where it is needed. So in many spaces, you know, we don't need an even wash of light everywhere. So, you know, this being an example, not indicating that this is necessarily bad in any way, but we can see some opportunities here. You know, the way this space is set up, all the activity happens right here on these desks. This is transition area. There's not a need to have the same light level on this desk as there is on this floor right here. In addition to that, we can see that every single workstation here has a task light. So there's also not necessarily a need to provide the full amount of light that you might need to perform every task by using the permanent architectural lighting system above you. You can have lower light levels and then rely on your task lighting to produce task illuminance in front of you. And you can almost guarantee that not all of these task lights are going to be on at the same time. Nothing is by focusing the light only on these desks, right? So you can see a situation where instead of having these kind of offset, you have your single row of lights over the spine of these desks right here. So it's focused on the work task here, and it's okay if we fall a little bit below down in here. And then also, of course, we want to be able to take advantage of day lighting, right? We need to be careful that we're balancing things because it can be very bright at the edge, and we don't want it to be, you know, 1/100th of the light level up here. But we want to be able to dim these lights that are up close to perimeters with day lighting. Another thing we can use is what we call, you know, high-end trim or lumen harvesting. So this chart represents the fact that all light sources will lose light output over time. Older technologies lost very quickly in comparison to LEDs, which LED doesn't actually burn out, right? So we had to define a life rating for an LED, and we chose this point where we've lost 30% of the light output from the LED. So L70 is what we refer to as a life rating for LED light sources. So what happens is, if you are planning for your light levels to be where you want them, say you want 30-foot candles over the life of the system, right? Our light output at the life rating is going to be here, right? 30% lower than full output. We need to design based on this light output. If that's all you're doing and you're not accounting for the fact that we're starting out with much more light output than we need, what you do is you end up with a space that for most of its life is illuminated higher than you need. That means you're using more energy than you need. Lumen harvesting is a process by which, of course, you design so that when you hit here, you're at your light levels, but we start by dimming the light. So we can dim it 30%. And over time, we raise the light level that comes up here until we hit our L70. And so all of this power under this curve and above this imaginary curve here, that's all power that we're not using, that we would have been using in the other case. So I refer to that as lumen harvesting. That has been done with fluorescent systems. It can also be done with LED systems. It just takes a sophisticated enough lighting control system to make that happen. We can also high-end trim light levels. IES recommendations are based on 70% of the population feeling comfortable under a certain light level. In many cases, we've worked with customers who, if we designed to a, say, a 50-foot candle level, they ratchet the high-end trim. So the high-end trim means we only produce 90% of the output. You know, we don't dim it to 100%. You can ratchet that down over time until you start getting people to say they're not comfortable, right? And a lot of people find that they can get down to 20% lower light levels by high-end trimming the lights. It saves you energy right off the bat. You want to provide manual dimming control in your spaces. You want to have definitely automatic daylight harvesting in spaces where there's enough daylight where you can dim the lights and still have enough light in the areas. And also you can time clock sweep at night. That includes emergency lighting. You know, if nobody's in the building, there's no need for emergency lighting to be on. So for sure, anytime a security system is activated, emergency lighting should go off. The most energy efficient light is the one that is not on. All right. So briefly talking net zero strategies, you basically take the strategies we just talked about and tighten the reins on them, right? So we can reduce the timeout period on our aux sensors. We can cap light levels at the minimum IES recommended levels. And then we want to have an ambient task system so that we have low ambient levels with task lighting, providing our task illuminance. And again, you can almost guarantee all the task lighting will not be on at the same time. There's also DC lighting systems. So sometimes it's called PoE, that's one type, where instead of having a driver in every single luminaire, we have one central driver that is pushing DC voltage out to all the light sources. You can save some of the losses in the drivers by using the DC system. All right, so I want to end up here. I know we're running tight on time, but I have 3 cases to kind of show you. So this case study deals with the fact that, we hear the term light gives form to architecture. That deals with the quality of light hitting a surface, right? So in this case, this space might be a pre-function area, maybe a transition area, or an entry lobby to a space. When we light it with diffuse lights, we of course provide all the task illuminance we need to get through the space. And we start to pick up some of the texture, say on this wall here. We start to see some of those. However, it's very diffuse, right? So it tends to flatten things out as well. By just changing the distribution of the lights, if we wash this, even graze it, and create these patterns of dark and light on the floor, we really bring out the texture of this wall. So it jumps right out at you. The motion you see that's elicited by this is very different than what we saw with the diffuse lighting. And both of these systems will produce enough light to get you through the space and perform the task you need. So that's an example of how light is giving form to the architecture. I also wanted to show a case where we're looking at, say, a classroom environment. The IES will recommend that we have, say, up to 40 foot candles if adults are in this environment. Oddly enough, if it's a K through 12, it could be as low as 20 foot candles, and that is what the light level should be at the desk. So showing a system here where we're using overhead, 2x4 troffers. This is actually rendered based on volumetric troffers. In this case, we're producing 37 foot candles at the top of the desk. The maximum light level we see across the space is 49, with the minimum 16. So our max to min ratio is 3.1 to 1, which is a very good ratio. It's a nice even illuminance across the surface. The teaching wall, which actually is this here in this image, right up about this level, we have 25 foot candles average. If anything, it may be a little bit spotty, right? Some areas are bright and dark, but still a good light level. So this actually, checks all the boxes. We've got enough lighting. We've got enough lighting on our teaching wall, and we can see very well in the space. Our lighting power density in this case, 0.34 watts a square foot. If we look at space by space allowances here, we can go up to 1.24. We saw another reference to 1.11, well below that with this system. Now, if we look at altering the lighting system in the same space, instead we move to a indirect direct system where we're illuminating the ceiling, and then we have maybe 20% light output coming out of the bottom of these luminaires. We look at the metrics in here, we have an average of 39 actually on the desk. The max is a little bit higher than the other case. The minimum is also a little higher. So our max to min ratio is still right about the same at this level here where our task level is. The teaching wall is a little bit lower at 21 foot candles, but still within the recommended levels that we would look for. One thing to note is this is actually a more even illuminance on this wall. The other thing I would note is the shadows under the desks here. Let's go back here. We can see are very distinct in this direct system. So what that also means is as you put your hands over the surface or your head, you're going to see some distinct shadows as well in the system. With an indirect system, the shadows are very much softened. And a totally indirect, you can put your hand 6 inches above a desk and hardly see a shadow at all on the desk. It's really pretty amazing. So what do we sacrifice? We sacrifice the lighting power density. So it pumps up to 0.5. However, I would say that this space looks maybe a little larger with our illuminated ceiling in this space. And, for a lot of people, probably more inviting because of that spaciousness. We're still well below the ASHRAE and ICC levels. Last one we're going to look at is the parking garage. And so, the IES actually has pretty low recommendations for the actual light level itself. It really focuses on max to min ratios. You don't want to be above a 10 to 1 max to min ratio on the ground in a parking garage. There are multiple tasks in here. Of course, you want to be able to see when you're driving. You want to be able to see pedestrians when you're driving around. There's also a huge safety factor when you're walking into a space, especially residential parking garages where, at all hours of the night, you might be going into the parking garage, get into your car, or walk out. You want to be sure that you don't feel unsafe and that there aren't dark pockets in the space. So this is an example of hitting our light level. In this case, we're at 5.3. We tend to design at the 5-foot candle light level average. So we have lights running down the center drive aisle, and these are linear enclosing gasketed lights, 4 feet each. Again, we see we're hitting a 5.3 average, which is what we like. Our max is 24.7 with a minimum of 0.8. And so our max to min ratio here is very high. It's 30.9 to 1. Yes, we're hitting our average level, but the max to min is really just too high. And if we took a vertical reading at a spot that was down here towards the front of your car, at about 5 feet above the ground, we're averaging about 1.3. Now, our lighting power density in this scenario is very, very low. It's 0.046. We're allowed 0.2. So we have a lot of space to roam. This is a very low lighting power density. If we look at an approach where we're taking now luminaires that are designed specifically for parking garages, and instead of running down the middle, we're alternating on either side of the drive aisle. We do end up with more luminaires in this case, maybe about 10%. And but what we see is our average is again 5.2. It looks way more even than what we saw here with the hot spots. Our max is at 17, so the maximum is what really dropped the most. Our minimum is 1.4 for our maximum at 12 to 1, which is still a little bit above the IS recommendations, but we can see it's much closer and it looks much more even across the entire space. Our vertical light level at the front of the cars now is 3.5, which is much, much better than, I think it was 1.3 on the other. Again, our lighting power density does come up, but it is still very, very low compared to what we're allowed to have. And so with this system, you create a better sense of security and safety as you're walking to your car. Okay, so that was all I had there. I know I'm running really tight here on time, so let me see if we have any questions piled up. So let's see. My questions window is very small. Okay, well, actually, I don't really have any questions. I just have a neat comment about the blind spot, which was a very fun experiment. So, all right. Well, with that being the case, again, thanks for everybody for attending. I really appreciate it. I love talking about this stuff, and certainly hope you will join us again in 2 weeks for the Geo Exchange for Residential Neighborhoods, our continuing series. This will be presented by Roger Frechette on August 5th on the same time slot from 12 to 1. All right, and that does it for me.
Scott, that was wonderful. Thank you very much. Really appreciate it. And thank you, everybody, for joining in. We will be distributing in an email that we'll be providing AIA certificates for anybody who provided their AIA number, but we will also send an email around which will include a link to a video of today's presentation. So thank you very much and have a great day.